Welcome back. So, in the last class, we started discussing about algorithms for constrained optimization problems, and in particular, we saw quadratic programs with linear equality constraints. So, for a given quadratic program where the Hessian matrix is symmetric positive definite matrix, which is the case in many of the practical problems. If we write down the Lagrangian and set its gradient with respect to x to 0, we get the first equation Hx plus A transpose lambda plus equal to 0, and the feasibility of x will ensure that x equal to b, and in this case we have n plus m equations in n plus m unknowns, and if in this case h is invertible. So, using that fact, we derived the solution for x to be this with the corresponding Lagrange multiple lambda obtained using this formula. Now, this being a equality constraint problem, the lambdas are unrestricted in sign, and then we saw a couple of examples where in this example the problem is to find out a circle of minimum radius which touches the line x1 plus x2 equal to 1, and as you can see here that the circle centered at 3 2 will touch this line at 1 0 and will have minimum radius. So, this is the optimal x. Now, we have similar problem, we are still looking for the circles of minimum radius centered at 3 2 which touch the line x1 plus x2 equal to 4, and as you can see from this figure that this is the solution. And similarly, we have another quadratic function whose contours are elliptical, and we are interested in those contours which touch this line x1 plus x2 equal to 4, and obviously the solution is this point. So, let us start looking at a general case where we have a quadratic program with a positive definite Hessian matrix, and there are some equality constraints and some inequality constraints. So, the equality constraints will be denoted by ai transpose x equal to bi, and inequality constraints will be denoted by ai transpose x less than or equal to bi. So, depending upon from which set the index I comes, there will be either equality or inequality constraints. Now, we want to devise an algorithm to solve this problem, and the idea is that given a point which is feasible, find out the set of constraints which are active, and once we have the set of constraints which are active, then solve the quadratic problem with respect to those active constraints. So, in that case we simply have to consider the equality constraint problem, and once we find the solution of that problem, we have to check whether that solution is in the feasible set or not. If it is in the feasible set, then at that point what are the new active set of constraints, and if it is not feasible, then we have to bring the solution back to the feasible region, and this process needs to be repeated till we get the optimal solution. So, this simple procedure is called active set method, and let us study this algorithm now. Now, if given a xk which is a feasible point at the kth iteration of the algorithm, let us define the working set wk to be the set of all equality constraints and the set of all inequality constraints which are satisfied with equality. So, the union of these two sets would determine the working set wk at the kth iteration. Now, having determined wk, the next step is to find the descent direction with respect to wk, and then we take a step along the descent direction by determining an appropriate step length, which is alpha k, which is a positive number. So, as we saw in the last class, the associated with wk, we need to solve the problem which is minimize half of d transpose h d plus gk transpose d where gk is the Hessian gk is the gradient of the objective function at the given point xk, and this is with respect to the constraint that ai transpose d equal to 0. So, it is easy to derive this program using our original program. So, if we substitute x by xk plus d here, and then to ensure the feasibility, we need to make sure that ai transpose d has to be 0, because ai transpose xk equal to b. Remember that the i's come from the set of active constraints or the working set at the iteration k. So, this is very important that this set would consist of all the equality constraints and some inequality constraints also, if it is possible to have some active inequality constraints at the given point xk. Now, if we solve this problem and we get dk to be 0, then what it means is that the current point xk is optimal with respect to wk. That means that there is no need to move from xk as far as wk is concerned. Remember that this is not the optimal solution with respect to the entire original problem, but it is optimal only with respect to wk. Now, in that case, we have to check whether the Lagrange multipliers corresponding to the inequality constraints which are part of the working set wk, whether they are non-negative, because as we have seen in the set of as we have seen when we discussed about the KKT conditions for the problem, we saw that at optimality the Lagrange multipliers of the inequality constraints are non-negative at optimality. So, we have to now check whether xk is optimal with respect to the entire original program, and for that purpose we need to find out what are the inactive constraints which are part of wk and whether the corresponding lambdas are non-negative. Now, if that is the case, if lambda I is greater than or equal to 0 for all inactive constraints in the working set, then we have solved the problem completely for the original quadratic program, because for the remaining inactive constraints which are not part of the working set, the lambda i's can be set to 0, and therefore, we have solved the problem. Now, if that is not the case, then what one has to do is that pick one lambda I which is non-positive or which is negative, and drop that corresponding constraint from the set wk to form wk plus 1. Now, if dk is not equal to 0, that means we are able to find a direction dk along which the objective function can be improved, then the next step is to determine the step length alpha k, such that xk plus 1, which is nothing but xk plus alpha k dk, is feasible with respect to all the equality constraints and all the inequality constraints. So, remember that every point that we generate in this algorithm has to be feasible with respect to all the constraints, and this is very important. And by moving to xk plus 1, if we have identified a new constraint or new inequality constraint which has become active, then we need to add that constraint to the set wk plus 1. So, these ideas will be more clear when we see some examples. For example, let us consider this problem which we have already seen. Minimize half of x1 minus 3 square plus x2 minus 2 square subject to the constraint minus x1 plus x2 less than or equal to 0 and x1 plus x2 less than or equal to 1 and minus x2 less than or equal to 0. Now, on the right side you will see the constraint set. So, this line corresponds to x1 equal to x2 and this line corresponds to x1 plus x2 equal to 1 and x2 greater than or equal to 0. So, which means the half space indicated by this arrow. So, we are looking at the intersection of half spaces indicated by this arrow and this arrow corresponding to the 3 constraints, and this is the shaded region which is given here. Now, what we want to find out is to find out a point which is or a circle of minimum radius centered at 3 2, which touches this feasible region. So, we are interested in finding out the circle of minimum radius which touches this feasible region. So, let us see how to solve this. Now, if you look at the Hessian matrix of this objective function, it is an identity matrix, and the C vector is shown here. Remember that we have put this objective function in the form half x transpose h x plus C transpose x, and in this case the Hessian matrix is a symmetric positive definite matrix. Now, let us start with an initial point which is the origin, that is a feasible point. As I said that at every iteration the point which is obtained has to be feasible with respect to all the constraints. Now, at this point we find out what is the gradient, and since x 0 is 0, the gradient is nothing but C. Remember that this gradient will be needed when we want to solve a problem to get decay, because in that case we have to solve a problem associated with the working set. Now, at 0 this constraint is active, the first constraint minus x 1 plus x 2 less than or equal to 0, and then third constraint minus x 2 less than or equal to 0, they are active. So, the working set at the 0th iteration is the first constraint and the third constraint. The second constraint, which is inactive, is shown here by dotted line. Now, if we solve the quadratic program associated with W 0, so W 0 is this working set, and if we solve that quadratic program, that is a equality constraint quadratic program, and it is easy to solve because we have already found out a way to solve a quadratic program with equality constraint when the Hessian is symmetric positive definite matrix. So, you can check that the solution to that quadratic program is d 0 equal to 0. So, it is easy to see that because if you take this constraint and this constraint, then this is the only point which is feasible as far as these two constraints are concerned, and therefore, that has to be the minimum point, and therefore, d 0 is equal to 0. And since d 0 is equal to 0, we look for the corresponding value of lambdas, the Lagrange multipliers of the inequality constraints which are part of W k, and those lambdas using the closed form solution that we saw earlier, those lambdas turn out to be minus 3 and minus 5, and both are negative, and therefore, we may have to drop one of the existing active constraints to form W 1. So, suppose we drop the constraint 3. So, constraint 3 is this constraint, and suppose we drop this constraint and retain only one constraint, which is x 1 minus x 2 greater than or equal to 0. So, if we retain that constraint, now for the next iteration our point x 1 will be still the same, but now we will be working with W 1 to be containing only one constraint, and that is the first constraint, and this is shown here. As you see here that the third constraint is shown by dotted line, which means that that is not an active constraint. The second constraint anyway was not active constraint at this point. So, the only active constraint that we are considering at this point is the constraint minus x 1 plus x 2 less than or equal to 0. So, our current point is still the same, and therefore, the gradient at that point is also still the same, but the working set is now only the first constraint. Now, with respect to that, we solve the problem to get d 1. and turns out that d1 is nothing but this direction where both the x1 and x2 components are 5/2. So it is this direction that we are considering. Now, if we consider this direction and if we set alpha 1 equal to 1, the step length, then what we get is x2 to be 0 plus this quantity, which is 5/2 comma 5/2. So, which is the point here, and clearly this point is not feasible point because we have crossed the feasible region here. So, in such a case we need to backtrack. So, we need to move back along that direction till we have a point which is feasible, and that is obtained by backtracking or setting alpha 1 to be 1/5 in this case to get x2 to be half, which is the point here, which at the intersection of these two constraints. Now, at this intersection, which has the coordinates half and half for x1 and x2, you will see that this constraint, the second constraint as well as the first constraint are active, and therefore, this second constraint gets added to the working set, and here is the situation where we have the current point which is having x1 and x2 coordinates as half and half, and the two active constraints are the first two constraints. The third constraint is an inactive shown by the dotted line. Now, this is the working set, and again with respect to this working set, if we solve the problem to get d2, you will see that d2 is equal to 0. So, d2 equal to 0 is obvious because since in two dimensional space we have two non-parallel lines, they intersect at a point, and therefore, that is the only feasible point. So, there is no direction that we can find to improve the objective function. So, d2 is equal to 0, and therefore, the next question to be asked is that which constraint can we drop if this point is not optimal. If it is optimal, then we will be done. So, now if we calculate lambda, you will see that lambda equal to minus half and 2. So, the first constraint has negative Lagrange multiplier. So, and the first constraint is the inequality constraint. So, certainly this point is not an optimal point, and therefore, we drop the first constraint and retain only the second constraint, and we are ready for the next iteration. So, at the next iteration, you will see that at this point, this is the only constraint which is active. This constraint is dropped, this constraint is dropped from the working set. Now, what is the next direction d that we should take with respect to this working set, so as to improve the objective function, and it turns out that that direction is this direction, and if we set alpha equal to 1, then x3 plus d3 will give us 1 comma 0, and that is the point x4, and that point is shown here, is the point 1 0 here, and that is the feasible point. So, it satisfies all the three constraints and it is a feasible point. So, alpha equal to 1 is a good choice here. Now, we have to check whether the Lagrange multipliers are positive, because we have only one constraint which is active here. We have to see whether the corresponding Lagrange multiplier is non-negative, and it is equal to 2, which is certainly satisfies the condition that lambda should be non-negative for active inequality constraints, and therefore, this point is the optimal point. So, if we trace the path that we obtained using this algorithm, you will see that we started from this point and then moved on to this point, and then from this point we moved on to this point, and at this point we found that the Lagrange multiplier of the active inequality constraints are positive, and therefore, we have got the minimum solution for this problem. Now, this was the case where we moved along the boundary and got the solution, but this need not always be the case. So, let us see another example. So, here is another example where the convex quadratic function is given subject to some linear inequality constraints. And if we draw the feasible region, so the constraint 2x1 equal to 2x1 minus x2 greater than or equal to 0 points in the half space shown by this arrow. The constraint x1 plus x2 less than or equal to 4 shows the half space given by this arrow, and x2 greater than or equal to 0 gives the half space indicated by this arrow. So, the intersection of these three half spaces is the shaded region which is shown here, and we want to minimize this objective function subject to this constraint. Now, since 0 is one of the feasible points, let us start with 0. Now, for this objective function, the Hessian is symmetric positive definite, but not a identity matrix. Now, if we start with x0 equal to 0, and at this point the two constraints which are active are the first constraint and the third constraint. The second constraint shown by the dotted line is inactive. So, as we saw earlier, that if we now determine the direction to be moved, we should get t0 to be 0, because that is the only feasible point as far as these two constraints are concerned, and therefore, we would like to find out which constraint should we drop from this, and that is done by finding out the Lagrange multipliers. So, if we calculate the Lagrange multipliers using the formula that we saw earlier, you will see that both the Lagrange multipliers corresponding to these inequality constraints are negative. So, we choose the one with the least value to be removed. So, the third constraint gets removed from the working set, and therefore, now the working set has only one constraint, which is the first constraint. So, the first constraint is here, and this is shown here in this figure, where only the first constraint is active, the other two constraints are inactive as far as this current point is concerned. Now, we are still at the point 0. So, x1 is still 0, w1 is 1, and then we solve the problem to get d1 associated with the working set w1, and that d1 turns out to be this direction 11 by 9, 22 by 9. So, this direction is given here. Now, if we take alpha 1 equal to 1, we get x2, which is this point, and that point one can check that that point is feasible, and the corresponding lambda, if we calculate, the corresponding lambda is negative, and therefore, we need to drop this constraint from the working set, and after removing that constraint, we get w2 to be a null set. So, now we will be at a point x2 where the working set is a null set, and this is shown here, where this is the current point that we have, where x2 is 11 by 9 and 22 by 9, which was obtained earlier, and the only although this point lies on this constraint, you can see that because that constraint had negative Lagrange multiplier, and that was the only active constraint at that point, we removed that constraint from the working set, and therefore, we are left with w2 to be 5, the null set. Now, we solve an unconstrained optimization problem to get the solution of this, because there is no constraint in the working set. So, solution of unconstrained quadratic program is the point 3 2, whose x1 coordinate is 3 and x2 coordinate is 2, and that point is shown somewhere here. So, which means that we have definitely crossed the feasible region or moved away from the feasible region. Now, in moving to that point, this direction was followed, and therefore, we need to backtrack to come to a point which is feasible as far as this constraint set is concerned. And therefore, that backtracking gives alpha 2 to be 1 by 4, and therefore, x 3 is equal to this point, which is having x 1 coordinate as 5 by 3 and x 2 coordinate as 7 by 3. Now, at this point, you will see that this is the only active constraint, which is x 1 plus x 2 equal to 4. So, therefore, that constraint is added to the working set. So, now we have this point, and now constraint 2 is added. So, which means that the constraint 2 is now active. We now are sitting at this point with this constraint active, and again we would like to determine the direction d along which we can move, and that direction turns out to be this direction. Now, how far should we move? So, if we set alpha 1 equal to 1, then x 4 is equal to x 3 plus d 3, that is equal to 7 by 3, 5 by 3. So, that is the feasible point. So, that is shown here, and x star is equal to 7 by 3, 5 by 3 in this case. Now, if you look at the path that we followed, so we started from this point, then came to this point. From this, we reached the point 3, 2, which was outside the feasible region. So, we backtracked, came back to this point, which is on the feasible region, and then at this point only the second constraint was active. So, we moved, we found out the direction d. That direction turned out to be this direction, and we took a step of unit length along this direction to come to this point. And at this point, if we check the Lagrange multiplier of this associated with this constraint, we found out that it is 2 by 3, which is positive. So, certainly this point is the minimum point. So, you will see that the active set method at any iteration tries to find out the set of constraints which could be active and solves the equality constraint problem with respect to those constraints, and this procedure is repeated till we get a solution. Now, since the number of possible active constraints is finite in number, this algorithm will definitely converge in finite number of iterations for convex functions, because every time we minimize the function, there is a decrease in the objective function, and the number of combinations or number of possible active constraints at any iteration is finite in size. Therefore, the number of ways of selecting the active constraints from the given set of constraints is also finite. Though it is exponentially large in number, it is still a finite number. So, for quadratic functions, convex quadratic functions, this algorithm can terminate in finite number of iterations. Yeah. So, let us formally give the algorithm for a quadratic program with linear equality and inequality constraints, which we are going to denote in short by QPLC, quadratic program for linearly constrained problem. So, H is a symmetric positive definite matrix, and E and I denote the set of equality and inequality constraints. And as I mentioned earlier, that at every iteration we need to find out a working set Wk and solve a problem to get the direction along which we need to move. So, given a feasible point xk and the working set Wk, the idea is to get dk by solving this sub problem. Now, as we saw earlier that there is a term, a linear term in the objective function which involves the gradient of the objective function at k, and the Hessian is constant. So, that is independent of k for a quadratic objective function. Now, AI transpose D is equal to 0 is a constraint where I belongs to the working set. Now, if we combine these AIs and put together in the form of a matrix A, so this program will look like the objective function is still the same, but now we have a compact way of writing this active constraints. So, AWKD equal to 0. So, the suffix WK means that we pick AIs based on those indices in the working set and put them in the form of the row of the A matrix or the columns of the A transpose matrix. So, this compact form of the sub problem we are going to denote it as QP sub. So, at every iteration we need to find out what is the working set and then solve QP sub. So, let us see the algorithm. This algorithm is called active set method, and the algorithm given here is to solve a quadratic program with linear constraints. So, we are given the input matrix H and C and the equality and the inequality constraints. So, they contain both AIs and BIs for the equality and inequality constraint. So, the first step is to initialize a point which is the feasible point. Now, this feasible point can be obtained by using phase 1 of simplex method, because we have the set of equality and inequality constraints. Now, those can be written in the form of equality constraints by adding some slack or surplus variables and artificial variables, and artificial linear program is solved to get an initial point x 0. The working set at that point is determined, the iteration counter is set to 0, and then the flag which denotes when to stop, that is set to 0. Now, while that stop flag is not set to 1, the first step of the algorithm is to get AWK, the AIs corresponding to the working set, and then solve the corresponding sub problem QP sub to get the direction dk along which we can move. Now, if dk turns out to be 0, then we check whether the current point is optimal, and for that purpose we need to determine what are lambdas. So, there is a closed form expression to get these lambdas based on the A matrix. So, here A is nothing but AWK, but to avoid notational clutter we have not indicated the dependence of A on WK explicitly in this expression, but remember that this A is same as AWK. And then we find out the minimum value of lambda among for all those inequality constraints which are active or which are part of the working set. Now, if that minimum value is non-negative, then we stop. So, stop flag is set to 1. Otherwise, the index q corresponding to which the lambda value was minimum, that constraint is removed. So, the active inequality constraint for which the lambda was the least and was negative gets removed from this working set. Now, if d is not 0, that means we have got a direction d along which to move. Now, the next step is what is this to find out what is alpha k, and for that purpose we need to find out whether the step size of 1 will cross the feasible region or not. So, if we compute this B I minus A I transpose x k by A I transpose d k for all those I such that A I transpose d k greater than 0, that gives us a clue. Now, if that quantity is less than 1, so that means that we do not have to worry about overstepping, but if that quantity is 1, then certainly alpha k can be set to 1, and which essentially means that we can take a full step of length 1 without worrying about the feasibility, and then x k plus 1 is set based on x k plus alpha k d k. Now, if this value was less than 1 or the alpha k value was less than 1, then that means that we are now at a point where the new constraint needs to be added to w k, and that is done in this step. Now, having done this, if stop lag is still set to 0, we increase the iteration counter and go back here. So, this procedure is repeated iteratively till stop flag becomes 1, and stop flag will become 1 when at a current point the Lagrange multipliers of the active inequality constraints which are part of the working set w k are non-negative, and that at that point we stop, and what we get is x star to be the value at the current iteration. So, this is the active set method, and for quadratic programs it is easy to show that this method converges in finite number of iterations, because the number of possibilities of active constraints is finite in number, although it is exponentially large. Now, these ideas can be used to solve a general nonlinear program. Now, if we consider a general nonlinear program, minimize f x subject to h j x less than or equal to 0, so j going from 1 to L, and E I x equal to 0, I going from 1 to M. Now, we have a general nonlinear program. Now, the active set method can be used based on the approximation of f as a quadratic function. So, if we approximate f x by a quadratic function at a given point and approximate these constraints by affine constraints at a given point, then we have at a given point minimization of a quadratic function subject to linear equality and inequality constraints, and we have already seen the active set method to find a solution of this problem. Now, one has to be careful about this approach, because there could be situations where one needs to take extra care. So, for example, suppose that we have an inequality constraint which is of this type. So, the shaded region denotes the so this side is the feasible region. Now, suppose that this is the current point. So, let us call this point as x k. Now, this is the constraint. We need to approximate this constraint by an affine constraint. So, let us show the approximation of this constraint to be like this. Now, at x k, let us assume that we have a direction which is minus g k. So, negative of the steepest descent direction for the function. Now, so far we talked about the projection of this negative steepest descent direction on the constraint set, but here we have to now talk about the projection of the steepest descent direction on the affine approximation of the active constraints at the current point. So, now if we project this we get a point. So, let us call this point as y. Now, you will see that this y is not active, y is not part of the feasible set, because the constraint is violated at the point y. So, what we need to do is that we need to find a point on this constraint set such that at that point all the descent conditions are satisfied, like the objective function decreases. So, one way to do that is move along the. So, if we take a point x k, take a tangent plane to the constraint set at the point x k and move along the direction which is perpendicular to that plane. So, if we move further, so we may come back to a point. Now, at this point we have to check whether the constraint is active, which is certainly the case, and whether the objective function has decreased sufficiently. Now, if it has not decreased sufficiently, what we may have to do is that we may have to move in the neighborhood of y, and so we may have to move along this direction and then find a point again in the direction perpendicular to a tangent plane to see whether the objective function is decreased, or we may have to go further and then come to this constraint set and then check whether the objective function has decreased. So, once we find a point, so suppose that this is the point where the objective function has decreased, then the next thing that one has to do is that we have to find out whether the working set has changed or not at this point. Now, it may so happen that we may have another constraint which is shown here. So, we may have another constraint. Now, this point has satisfied the condition with respect to the original constraint, but as far as this new constraint is concerned, this point is violating that feasibility constraint, feasibility. So, we again need to backtrack till we come to a point where with the point somewhere here, where if we project it onto this, then we satisfy both the constraint. So, the method becomes more and more difficult because the projection is on the tangent plane, and from there one has to move to the curve, and then at that point we need to check whether no new constraints are added. So, the procedure becomes more and more difficult, but there exist some other methods which could be useful for solving such problems. Now, another disadvantage of the active set method is that one needs to find out a proper combination of active constraints to get the solution. So, we started with this combination of active constraints, and then we have to move through another combination finally to get a solution. So, the number of combinations of active constraints is, though finite, it is exponentially large in number, and therefore, finding the correct subset of active constraints from the given set of constraints is always a difficult task. And the second point that we need to note here is that all the points which are generated always lie on or inside the feasible region. That means, we are not allowed to deviate at any point of time from the feasible region. Even a deviation which is very small is also not allowed. So, we always have to remain in the feasible region, and that could be a disadvantage in some cases. So, it may so happen that we might have got a solution by visiting only a small number of points or in a shorter time if we had not used active set method. So, there exists some methods which are not directly associated with the set of active constraints at any point of time, but they work in the entire n dimensional space and solve the original problem. Now, this was the path traced by the active set method, and you will see that one has to go to this vertex and then to this vertex to reach this solution. But are there any better ways of solving this problem? So, let us look at some of those methods. Now, those methods are called barrier and penalty methods, where we do not have to worry about finding the active set at any point of time, and these methods also find points as the iterations progress, which could be away from the feasible region, but when the algorithms converge, one will have found a point which is close to the optimal point in the feasible region. So, let us consider a problem of this type to minimize f x subject to the constraint that x belongs to the set x, which is a subset of R n. Now, the idea in this barrier or penalty methods is to approximate this constraint problem by an unconstrained problem. But then the approximation is not based on only one unconstrained problem, but there will be a series of unconstrained problems which will be solved, and the idea is that at every time when we find the solution of an unconstrained problem and take the sequence of such solutions which are formulated, then we will see that that sequence of solutions will converge to the solution of this problem. So, a sequence of unconstrained problems is solved, and that will give us a sequence of solutions of these unconstrained problems, and that sequence is expected to converge to the solution of this problem. So, the two methods differ in the way they design this unconstrained problem. So, the penalty methods, as the name suggests, they penalize for violating a constraint. So, a violation of a constraint is allowed, but there is a extra penalty or extra cost associated with this violation, and the penalty methods are based on that. The barrier methods, on the other hand, they do not let the feasible point move away from the boundary of the feasible region. So, one can think of it as putting a barrier around the boundary, so that the feasible points generated are always in the interior of the feasible region. So, these methods can also be thought of as interior point methods for solving constraint optimization problems. Now, if you look at this optimization problem, minimize f x subject to the constraint that x belongs to the set x. Now, suppose if we define a function psi x which is 0 in the space where x is belong to the set x, and it is plus infinity if x does not belong to the set x. And if we define such a function and then define a new function to be f x plus psi x, Now, one can see that if we minimize f x plus psi x, this problem is equivalent to the original problem. The reason is that if x star is the solution to this problem, then certainly x star belongs to x, and since x star belongs to x, psi x star will be 0, and therefore, we have got the minimum solution. So, any solution of this problem will be same as the solution of this problem, because since we want to minimize a function, the minimum of this occurs when x belongs to the set x, and once x belongs to the set x, then this term does not have any role to play in this minimization, and then it just amounts to minimization of f x. Now, if you think of this function, so let us consider a simple problem. So, let us consider a problem say to minimize x square subject to the constraint that x belongs to 1, 2. Now, on the real line, so this is the 1 and 2. Now, f x is equal to x square. Now, let us look at how the psi x would look like. So, if we consider psi x is 0 in this region and goes to plus infinity in this region. Now, so if we minimize first of all, if we want to minimize this f x plus psi x, where psi x is plus infinity on the boundary of this feasible region, you will see that numerically it is not possible, because plus infinity cannot be indicated using a number in a computer. So, even if you replace plus infinity by very large numbers, still the problem is that this function is discontinuous, because it is 0 in the feasible region, but then goes to plus infinity at the points which are outside this feasible region, and therefore, this function is discontinuous. So, since the function is discontinuous, that problem cannot be solved so easily. But suppose we design a function so let us design a function which is this is certainly not a good approximation of the function that we are looking for. What we are looking for is that once we move away from the boundary, the function, the psi x function should go to infinity. Now, the original function that we saw was not discontinuous, was discontinuous. So, therefore, we have designed a new function which is continuous, but which is not a good approximation. So, suppose psi x takes the form like this, we might not be able to solve the actual original problem. So, what one can do is that generate a sequence of functions which are continuous and which finally can be good approximations of the function psi x. So, such functions if we start using them, so initially suppose if we use this function, then we use this function in this direction, finally we will get a function which is very close to the function psi x that we are looking for. Now, this is one approach, this is called the penalty function approach. Now, the other approach is the following, that we have now what we do is that we use a function which is like this and then keep on changing the shape of this function, so that finally it is a good approximation of the function that we are looking for. Now, during this process you would see that we are penalizing heavily as we move towards the boundary, right. So, if there is a way to control these functions, so that if we move along this direction, the functions that we get are good approximations of the function psi x that we are looking for. So, these are called the barrier function methods, because they do not let the feasible point move towards the boundary. So, one starts with a point which is in the interior of the feasible region, and then one gets a solution, but the barrier functions will ensure that there is an extra or heavy penalty that one has to pay while moving close to the boundary. So, these methods are called penalty function methods or barrier function methods, and we will see more about them in the next class. Thank you.